our dynamic equilibrium unit review, which is question 13 or 14. 14. All right. So we're going to read through this carefully, and then we're going to see what we can do. All right. So question says we have some reaction. Okay. It's at equilibrium. That seems maybe it's important. And then we know it contains a mole of hydrogen, 2 moles of carbon dioxide, 2 moles of carbon monoxide, and 2 moles of water. And that's in a 2-liter bowl. All right. Question 1 says, can we find the value of the equilibrium constant? Okay, let's find out. So notice it says the value of the equilibrium constant, not the expression. So expression would look like this. And so if we found the KEQ expression, that would just be carbon dioxide times hydrogen over carbon monoxide times water concentration, and that is the equilibrium constant expression. Now, if we take these values and we find their concentrations, and we actually find a value for this ratio of reactants over products, then we have found the value of the equilibrium constant. Okay, so let's just try here. So what do we got here? Carbon dioxide, 2 moles, 2 liters. So that means 1 mole for every liter. And then H2, we have a 1 mole for every liter. Nope, 1 mole for every 2 liters. That means 0.500 molar. That's all over our 2 moles for 2 liters, so that's 1.00 molar for carbon monoxide, and 2 moles of water for every 2 liters, pardon me, and so that's 1.00 molars for water as well. Now we don't really care about the units, so we'll just ignore those. And also we have 1 divided by 1. Actually, the whole KQ value just simplifies, 0.500. And that is the equilibrium constant, or the value of the equilibrium constant. Okay, that's question A. How does 14b differ? 14b says now we're going to add some more hydrogen to the system. Okay. So I got something underneath this page. It's a staple. All right. Calculate the carbon monoxide concentration that will exist when equilibrium is regained. The carbon dioxide concentration when equilibrium is regained. So that sounds like an equilibrium concentration. However, this is going to contribute to some initial concentrations. Initial. So when you're comparing initial values of initial concentrations to equilibrium concentrations, that tells me we're going to need a rice table to answer that, a rice box. So let's go with a rice box. Let's draw one out. So RICE, our reaction is carbon monoxide plus water gives us carbon dioxide plus hydrogen gas. Now, each of these substances are original initial concentrations, except for the hydrogen. The hydrogen is going to be a little different. We're going to add another mole here. So I already calculated these concentrations for everything else. So for water, it was 1.00 moles. So it's going to be 1.00. Carbon monoxide, we calculated it to be 1.00. For carbon dioxide, it was 1.00. And for H2 concentration, that's going to be our original 1.00 moles plus our new 1.00 moles all over our volume, which is 2 liters, which is going to give us 1 molar. Okay. Now we need to find out the change in concentration. Well, we're not sure. But if it was in equilibrium before and we added some extra hydrogen, that means we're going to shift equilibrium to the left, and we're going to lose some of these guys in a 1-to-1 ratio, and we're going to add in a 1-to-1 ratio some carbon monoxide and some water. This is going to give us an equilibrium concentration of this value for each of them. Okay, that's fine. All right, and what were we asked for? We were asked for the concentration of carbon monoxide at equilibrium. So can we find out how big this actually is? That's what we're asked. To do that, we're going to use our equilibrium value, our concentration, our equilibrium constant, pardon me. So that's equal to 0.500, and that's going to be equal to the concentration of our new equilibrium, right? Products over our reactants, 1.00 minus x, 1.00 minus x, over 1.00 plus x, 1.00 plus x, which is another way of saying 0.500 is equal to 1.00 minus x squared over 1.00 plus x squared. The same thing as saying it's 1.00 minus x over 1.00 plus x all squared. Now, no matter how you slice it, you got to square root to undo that. And so we're going to square root a half, which is like 0.707 or something. Yeah. And that's equal to 1.00 minus x over 1.00 plus x. Now we got to solve by multiplying both sides by 1.00 plus x. It cancels it out, and we'll multiply by 1.00 plus x over here. And distribute the 0.707, so we get 0.707 plus 0.707x is equal to 1.00 minus x. So I'm going to add my x's so that they're positive. It's 1x. Take away 0.707. And we'll cancel out the things that cancel out here. All right. So that looks like I get 1x plus 0.707x, which is 1.707x. And that's equal to 1 take away 0.707, which is, I don't know, 1 take away my answer. It's 0.293. And to find my x, I'm going to divide by 1.707. And that tells me my x value finally is equal to, divided by 1.707, I get 1.72. Now, that's not what I was asked for. I wasn't asked for x. We're not done if we've found x. What is x anyway? That's a change in concentration, so it's going to be in units of molar. And if I want to know the concentration of carbon monoxide at equilibrium, that's equal to 1.00 plus x, which is equal to 1.00 plus 0.172, which is equal to 1.172 molar. And that is it. All right. Good luck studying. Please let me know if you have any questions about any of these. The rice box questions, there's lots of practice you got for these. Good luck with studying for your test.